Hi everyone, today we from the MSE 4335 Group 4 Development Team will be discussing about smart bioimplants. So just a quick overview of it, smart bioimplants have some advantages over classical implants since they heal the human body more naturally, so they provide fast treatment and also negligible complications. And they owe it due to the similar morphology that they have to the tissues that we have in our bodies. Hope you enjoy the video.
Throughout history, bioimplants have become of great significance in improving the longevity and quality of human life. They first appeared as early as 4 millennia ago when the Egyptians and Romans used wooden toe replacements and golden dental applications. However, it was not until the late 18th century that this practice was used in the science of implantology. In modern society, it is estimated that about 90% of people over 40 years old suffer from degenerative and inflammatory diseases which lead to immobility and chronic pain. In addition to the elderly, the younger, more athletic demographic is likely facing the same scenario due to sports-related injuries. The field of bioimplants continues to evolve as the technology behind biomaterials marches forward. Reviewing the properties of biomaterials is important for the proper selection of a specific application. Classes of biomaterials include metals, polymers, ceramics, and composites. The material chosen depends on the property needed, for example, flexibility, stiffness, and biocompatibility, to name a few. Today, researchers are developing smart bioimplants. Smart bioimplants use specific responsive materials in order to adapt to the environment. Changes in environment can include shifts in pH, concentration, temperature, stress, and other external factors. These stimuli will then alter the structure of the material, and the material will respond by adapting accordingly.
There's a lot going on within our products, so first let's look at some of the basics which make these high-tech bioimplants work.
Things today are getting smaller and smaller. So is the trend in the development in bioimplant. When you shrink materials into smaller and smaller parts, they will start to behave differently. The fundamental changes from these characteristics are the basis to develop and create these smart implants. For example, when in the case of nanoparticles, you have a lot of ways to modify the shape and size of the nanoparticle. Usually, this involves using organic ligands to develop your nanoparticle. When reducing your positive metallic nanoparticle using reductants, you can add ligands to add functionality to your nanoparticle. What does this mean? Imagine you are going to develop an artificial organ. With nanoparticles, you can produce membranes that have the same function as the cell membranes in the human organs. Today, diabetes is one of the top causes of death in the world. With the application of nanomembranes that have selective permeability, we can cure this disease no matter how serious the condition is. However, despite the potential shown by nanomaterials, a serious challenge posed to researchers is the biocompatibility of bioimplants. Biocompatibility is a property of implant materials to show favorable response in a given biological environment in a particular function. This depends on the corrosion resistance as well as the cytotoxicity of corrosion products. There are multiple corrosions that can affect how well the bioimplant fits into your body. This includes corrosion and corrosion resistance, which is the loss of metallic ions from metal surfaces to the surrounding environment. There are several types of corrosions that can be seen, which includes crevice corrosion. It occurs in narrow regions like implant screw bone interfaces. When metallic ions dissolve, they can create a positively charged local environment in the crevice, which may provide opportunities for crevice corrosion. There is also pitting corrosion, which occurs in an implant with a small surface pit. In this, the metal ions dissolve and combine with chloride ions. Pitting corrosion leads to roughening of the surface by formation of pits. Additionally, there is galvanic corrosion. This occurs because of the difference in the electrical gradients of materials. Nickel and chrome ions from artificial prostheses may pass to peri-implant tissues due to leakage of saliva between implant and superstructure. This may result in bone reabsorption and also affect the stability of the implant and eventually cause failure. Lastly, there is electrochemical corrosion. In this, Anodic oxidation and cathodic reduction take place, resulting in metal deterioration as well as change transfer via electrons. The type of corrosion can be prevented by the presence of a passive oxide layer on a metal surface. So how do we accomplish all those properties for a bioimplant? The answer to this lies in surface modification. The purpose of surface modification is to retain the key bulk properties of the material while modifying the surface to improve biocompatibility. Typically, modifications can either alter the atoms, compounds, or molecules on the existing surface chemically or physically, or coating the existing surface with a different material. The following are some of the important surface modifications.
Polymer brushes. Attaching polymer brushes is a method to modify the surfaces of these implants. The concept of brushes is that you can put polymers on the surface through physisorption or with thorough grafting and covalent attachment. Brushes on surfaces have an advantage of adding functionalities to the surface, but more importantly, they can also be modified to adapt to the environment by changing their polymer conformation through surface density, topography, surface energy, and others. The brushes can act as a method to modify the pores based on the environment, and highly modified brushes can even be used for natural or intuitive sensors. Chemical treatments. Chemical reactions can be categorized as specific and non-specific types. If the result of a chemical reaction is a distribution of different functional groups on the surface, then it is a non-specific reaction. Common examples of non-specific reaction include the oxidation of a polyethylene surface by chromic acid and radiofrequency glow discharge, albeit RFGD. When a surface reaction changes one functional group into another with few side reactions and high yield, it is called a specific chemical reaction. Alkylations and conversion to a siloxane come under this category. Ion beam implantation. In this process, accelerated ions are injected into the surface of a material, and the surface properties of the material are modified, largely used for metallic biomaterials. The process involves the implantation of the desired ions at high kinetic energies on a localized surface zone. Applications of such a process include improvement in hardness, wear, corrosion, toughness, and bioreactivity. One example shows that silver ions implanted into polystyrene allow cell attachment onto the surface. There are many materials that serve really well for some of the requirements for bioimplant materials, but it is not very good for others. For example, calcium phosphide-based ceramics show a great deal of biocompatibility, but their undesirable mechanical properties like brittleness, low strength, and low fracture toughness have limited their applications in load-bearing cases.
Other than performing surface modifications, we can also change fundamental material properties of implants such as elastic properties to best serve its function. For example, orthopedic implants are often engineered to have a Young's modulus and Poisson's ratio close to bone. Having appropriate elastic properties prevents biomechanical consequences. According to the principle of composite beam analysis, when two materials with different elastic moduli, such as bone versus titanium, are placed in contact and one is subject to a load, the greatest stress is localized at the first point of contact between the two materials. This can lead to stress shielding, known for its reduction in bone density, and bone resorption, the breakdown of tissues in bone. Bone tissue has an elastic modulus of 17 gigapascals and a Poisson's ratio of 0.3, so knee replacements are made to have similar numbers. A femoral prosthesis and tibial tray made of cobalt molybdenum alloy have elastic moduli between 70 and 80 gigapascals and Poisson's ratio of 0.3. A new type of elastic property being used in implants are materials with shape memory properties. One type of implant which uses a special property is a TAVR, a transcatheter aortic valve replacement. Previously, TAVRs were built with stainless steel frames, such as the Edwards Sapien valve. It is able to be expanded with balloons at a procedure called aortic balloon valvuloplasty. There is currently research being done on the development of a new TAVR with a supraelastic nitinol frame. One example of this is the Medtronic core valve.
In the procedure, a physician makes a small incision and inserts the device, which is less than 1/4 of an inch wide, into the artery in the leg. It is then guided through the arteries to the site of the narrowed aortic valve in the heart. Its small delivery system makes it possible to treat patients with a vascular system that is small or difficult to navigate. Once in place, the core valve system's self-expanding frame enables physicians to deploy it in a controlled manner, allowing for accurate placement. Here the device expands and takes over the original valve's function to ensure that oxygen-rich blood flows efficiently out of the heart and circulates throughout the rest of the body. The catheter is then removed from the patient's body and the incision in the...
Nitinol has shape memory properties. At warmer temperatures, including body temperature, nitinol forms a very strong primitive cubic crystal structure referred to as austenite, which has a high radial strength. Here we show an example of a flower made of shape memory alloy. The petals can be opened and closed with hot and cold air. This allows the stent to be tightly compressed in the delivery sheath, but when deployed in the body's warm temperature environment, it remembers its original shape and expands to fit snugly into the valve. As you can see, elasticity provides many beneficial features for medical devices, and we look forward to see what other devices shape memory properties will be used in the future.
2, 1.
Now let's take a look at the latest biosensors.
In the past, measuring biological structures, both internally and externally, has employed many often bulky devices. Currently, a new genre of biosensing devices that use very thin layers of various sensors can be used for a wide range of applications. This emerging technology can aid in the detection of electrical, mechanical, and chemical signals from the body. There are a variety of different circuit elements that can be used, such as organic or inorganic matrix arrays, graphene, nanotube or nanowire assemblies, and hybrid composites. These flexible sensors have a few advantages. They can be highly sensitive and multifunctional depending on the parameters. They also have high bendability and elasticity, which makes them very good for biological applications on organs or tissues as it develops. They also have cheap electrodes which can be manufactured with a geometrically controlled shape. A simple application of a biosensor is a sensor for the mouth. These biosensors use nanoparticles in order to obtain their high precision. These metal nanoparticles are dispersed in polymer systems so that their sizes and shapes can be controlled through the thermoplastic properties of the polymers. They provide enhancements in polymer conductivity by several orders of magnitude, as well as enhances applications for molecular detection for a wide variety of biological molecules. You can use these as a regular sensors or bioimplants inside the mouth to detect your food intake or saliva condition. The polymeric structures developed have been used for biochemical sensing, environmental monitoring, and also microelectric applications. Some sensing and remediation applications use polyomic acid, silver nanoparticle composite membranes, polyoxydinyl films, electrochemical disposition on gold nanoparticle films, and they're all functionalized on conducting polymer substrates. Other applications of sensors can be used for electronic skins or implants to our organs. Highly sensitive flexible pressure sensors were developed by joining microstructured PDMS dielectric layers that were used in the fabrication of electronic skins that mimic the tactile sensing properties of natural skin. Both the sensitivity and pressure range are adjustable by changing the shape of the PDMS structures, and this system exhibited high pressure sensitivity.
Now let's see some of our more advanced solutions for spinal injuries.
Today, carbon nanotubes are one of the hottest nanomaterials in the field of material science, and it shows no exception in the application of bioimplants. Carbon nanotubes have dimensions and properties that's similar to specific compartments of neural machinery. Here we can see that the typical diameter of carbon nanotubes is anywhere on the range of 1 to 2 nanometers. They have been shown to govern synapse formation, cell excitability, as well as synaptic processing. The recent rise of nanotechnology has allowed for the development of new generations of nanomaterials that are able to interface neuronal network formation and signaling with unprecedented abilities. Thus, implantable devices and materials hold a tremendous promise to overcome the effects of central nervous system lesions and disease. In particular, the use of carbon-based nanomaterials has a great potential for neurological applications. Here we can see the benefit and impact that the use of carbon nanotubes can have as an implant. We see on the left that natural neuroregeneration occurs in the spine. However, once compared to that of neural regeneration using carbon nanotubes, we can clearly see the difference that they have on impacting cell growth. The 3D mesh of carbon nanotubes are synthesized using a technique that is called chemical vapor deposition. Chemical vapor deposition is a process used to deposit solid materials onto a substrate whereby a monomer is vaporized and injected into a heated chamber containing a cooled substrate. So this will address specifically the creation of a 3D mesh of carbon nanotubes using chemical vapor deposition. Initially, ferrocene is dissolved in ethanol and injected into the growth chamber at a rate of 7 milliliters per hour, along with a hot flux of argon and acetylene, which act as the gas carrier and carbon precursor, respectively. Once all the reactants are present in the chamber, the specific chemical reactions are then allowed to proceed. As the chemical reactions proceed, these precursors will diffuse down the reactor so that they interact directly with the substrate. Once at the substrate, these precursors are absorbed and lead to the new creation of a thin film. These thin films are created once the precursors have homogeneously diffused across the surface of the substrate. The hot gas naturally forms a coating on the cooler substrate and the polymerization is allowed to progress, creating the mesh of carbon nanotubes. Once the film or mesh of carbon nanotubes has been created, the byproducts of the polymerization undergo desorption. Lastly, these desorbed byproducts are vacuumed out of the reactor to leave only the thin film of carbon nanotubes. These 3D meshes that are created using chemical vapor deposition are composed of a series of carbon nanotubes that are randomly oriented, as we can see here. However, for the use of these 3D meshes as a bioimplant, further functionalization must be added to these carbon nanotubes. The 3D scaffold is functionalized to facilitate a greater rate of reactivity once implanted into the body. This functionalization occurs to the physioabsorption of 4-hydroxynonenal. The physioabsorption occurs through what we know as weak van der Waals forces. The 4-hydroxynonenal is a bioactive molecule that allows for more extended and branched creation of dendrites and axons. Now that we've considered how the 3D meshes are created, we must consider what properties of carbon nanotubes make them such ideal scaffolds for a bioimplant. One such property is the exceptional electrical conductivity of carbon nanotubes, which is conducive to rehabilitating the lost function of segregated neural segments. Carbon nanotubes are great electrical conductors because of its chemical structure. When we consider the carbon atom, we see that it has a total of 6 electrons, with 2 in the inner shell and 4 in the outer shell. Thus, the 4 electrons in the outer shell are available for chemical bonding. However, as mentioned, since the carbon is only bound to 3 other carbons, these bonds are sp2 hybridized, leaving what is called a free electron. This sp2 hybridization leads to one free electron that is coined the pi electron, which overlaps to create pi bonds throughout the carbon nanotube. Due to the fact that these pi electrons are not localized, carbon nanotubes have an incredible electronic mobility. Thus, again, they represent an ideal scaffold for the growth of neurons due to its ability to facilitate electrical connections. Further looking at the chemical structure of carbon nanotubes, we see that when you compare the sp2 bonds to the sp3 bonds of carbon nanotubes, the bond energy increases from 86 kilojoules per mole to 150 kilojoules per mole. This makes it incredibly hard for the 3D mesh of carbon nanotubes to be irreversibly deformed. Additionally, carbon nanotubes also have a very high Young's modulus, meaning that they are able to withstand high stresses leading to deformation and bending before fracture or failure of the implant. This is crucial for an implant around the spine since the spine is always moving. Thus, we need a material that is able to withstand the stresses associated with that movement. With such a high Young's modulus, the 3D mesh of carbon nanotubes represents again an ideal material for. So while we have discussed why carbon nanotubes would represent a great scaffold for neural regeneration, we still must consider the biocompatibility of this material. To study the biocompatibility, the 3D mesh of carbon nanotubes was implanted into the brains of 4 adult male rats. Initially, the scaffold was immunolabeled for the glial fibrillary acidic protein, or GFAP. The GFAP fluorescence intensity peak was limited to a relatively restricted reactive area of less than 20 micrometers, which is smaller than other artificial implants which average a reactive area of 60 to 100 micrometers. Additionally, the ionized calcium binding adapter protein, IBA1, was also studied. IBA1 represents a protein that is expressed in microglia and is upregulated following nerve or tissue injury. It was found that IBA1 reactivity was low, and although it was found inside the scaffold, no scar-like formation occurred. To study the long-term effects of this implant, the same study was conducted with the rats, but they were sacrificed at different time periods, ranging from 0, 1, 2, 4, and 8 weeks. 8 weeks after implementation, the GFAP reactive area was seen to be even smaller than it was at 4 weeks. IBA1 microglia reactivity was slightly increased after 1 week, but this is likely due to the initial inflammatory response to the compressive tissue damage induced by introducing the material itself. After 2 weeks and up until 8 weeks, the IBA1 microglia reactivity progressively declined towards normal values. Thus, the results from both of the biocompatibility studies suggest a successful integration of the implant with the tissue. So in conclusion, due to the ability of carbon nanotubes to facilitate electrical signals across neurons, as well as due to their high tensile strength and elasticity, a 3D mesh of carbon nanotubes presents an ideal scaffold or frame for neurons to regenerate, all without compromising biocompatibility. And those are just some of the bioimplant products that have changed the lives of many people. Lastly, let's see some of the prospects of bioimplants in the future. As you all might know, the aging population in the US is gradually getting larger and larger due to recent medical advancements, so bioimplants will definitely have a high demand in the future. One of the most interesting developments of bioimplants is the development of long-lasting, non-hazardous batteries for electronic implants within our body. Besides the use of these batteries for classical implants, researchers are also looking at the prospect of therapy and treatment of conditions through electrical stimulation. Besides that, biocompatibility and biodegradability will always be an important topic in bioimplants. Cost will also always be a problem, which is why we hope to provide the best service with the lowest rate possible. We hope you enjoyed this video. See you soon.